These are the answers to the Chapter 14 packet, Chemical Kinetics. The term reaction rate is defined as the speed at which a chemical reaction occurs, and the term reaction mechanism is a step-by-step molecular level view of the pathway from reactants to products. Section 14.1, Factors that affect reaction rates. List 4 factors that will cause the reaction rate to change: the physical state of the reactants, the reactant concentrations, the reaction temperature, and the presence of a catalyst. Explain why 10 grams of powdered zinc will react with hydrochloric acid more quickly than a solid zinc strip that weighs 10 grams. Well, the powdered zinc has greater surface area than a strip of zinc, and the greater surface area means more collisions between reactant particles and a greater reaction rate. Explain why a sample of magnesium metal will react more quickly in 10 molar HCl than it will in 1 molar HCl. A higher concentration of acid means that there are more collisions between reactant particles and a greater reaction rate. Explain why an Alka-Seltzer tablet will dissolve more quickly in water at 80 degrees Celsius than in water at 20 degrees Celsius. A higher temperature means that there is greater kinetic energy, particles are moving at a faster speed, there are more collisions between reactant particles, and a greater reaction rate. Describe the role of a catalyst in a chemical reaction. A catalyst speeds up a chemical reaction without itself being used up. As the frequency of collisions between reactant molecules increases, the rate of a chemical reaction will increase. Section 14.2, Reaction Rates. What unit is used to measure the rate of a chemical reaction? It's normally molarity per unit time, so molarity per second or molarity per minute. In order to determine the reaction rate, the concentration of a reactant or a product is measured over time to see how fast it changes. The table below is based on the chemical reaction A goes to B, so because there is a 1-to-1 molar relationship between A and B, we can see that the sum of the moles of A and the moles of B would equal 1 in each column of this table. So when the number of moles of A has decreased to 0.73, that means that the number of moles of A that has been consumed is 0.27, and therefore 0.27 moles of B have been produced. As we continue to see the disappearance of A over time and the formation of B over time, the total number of moles is the same at 1. So we have 0.46, 0.60, 0.70, 0.79, and finally at 60 seconds we have 0.84. And so now we can actually create a graph showing the change in concentration of A over time. So the concentration of A is decreasing over 60 seconds, and the change in the concentration of B over time as it is being produced over this same 60-second period. Now the average rate of a reaction can be calculated for a particular time interval if we can figure out the change in concentration of a particular chemical divided by the change in time. So in this case we have a change in concentration for A, where a minus sign indicates that the concentration is decreasing. In the first 10 seconds, the change in concentration of A would be 0.27. In the next 10-second period, it goes from 0.73 to 0.54. That's a difference of 0.19. Then when it changes from 0.54 to 0.40, that's a difference of 0.14, a difference of 0.10 in the next 10-second interval, a difference of 0.09, and finally between 50 and 60 seconds that would be a difference of 0.05 moles per liter in that period. So if we divide all of these numbers by 10 seconds and we add a negative sign to show that it's disappearing over time, so it's decreasing, what you can tell is that the rate of disappearance of A over this particular 10-second interval as we go is decreasing. So examining the values for this average rate, the values for average rate are decreasing over time. Why would this be typical for a reaction rate to decrease over time over the course of the reaction? Well, the simple reason is that as the reaction proceeds, the concentration of the reactants themselves is decreasing, and therefore the reaction rate should decrease over time. So a higher concentration would normally mean a faster reaction rate, but here we have a lower concentration of the reactants, so the reaction rate is decreasing. The term instantaneous rate of reaction would mean that the rate of the reaction at a particular instant, and the instantaneous rate at time equals 0 is called the initial rate of the reaction. Suppose that in a certain reaction, the change in concentration of A over time is equal to twice the amount of change in concentration of B over time. So which of the following reactions is consistent with this rate information? If the change in A over time is twice as much as the change in B over time, then molecules of A are disappearing at a faster rate, so twice as fast as compared to B. So if I want 2 moles of A consumed for every 1 mole of B, I would choose the reaction on the left. So if we know the stoichiometry from the mole ratios in the balanced chemical equation, then we can convert from the rate of one chemical to the rate of another. At a certain moment in time, the rate of formation of hydrogen, which is a product, is equal to 1.8 times 10 to the negative 6 molarity per second. Well, the rate of disappearance of hydrogen iodide must be twice as much as the rate of formation of hydrogen, simply because 2 moles of HI are consumed for every 1 mole of hydrogen gas produced. So based on the reaction coefficients, the magnitude of the rate of change for HI should be twice as much as the rate of formation of hydrogen. We have to change that number, 1.8 times 10 to the negative 6. We have to double that, and we have to give it a negative sign to show that the concentration of HI is decreasing over time. So the correct answer is negative 3.6 times 10 to the negative 6 molarity per second. So in this graph, we have 2 lines that are increasing over time, and we have 1 line that is decreasing over time. So this is concentration versus time. Well, the only chemical that should be disappearing over time is the reactant, which is A. But then we have 2 different products, B and C, and they are forming at different rates because 2 moles of B are being produced for every 1 mole of C being produced. So since B has the same coefficient as A, then that particular curve should be the formation of B over time, and then C would be half as much. So that particular curve is increasing, but at a rate that is half as much as the rate of formation of B. All right, section 14.3, concentration and rate laws. We're looking at a table which shows initial concentration of ammonium and initial concentration of nitrite, and then we have the observed initial rate in units of molarity per second. In experiments 1 through 3, the independent variable is the concentration of the ammonium. So what's being held constant is the concentration of nitrite at 0.2 moles per liter. So the relationship between the independent variable and the dependent variable, reaction rate, is the following. In experiments 1 and 2, they have doubled the concentration of ammonium, and we have doubled the reaction rate. Comparing experiments 1 and 3, they have quadrupled the concentration of ammonium, and they have also quadrupled the initial reaction rate. Now in experiments 4 through 6, you can see that the ammonium is held constant at 0.2 moles per liter, and they're changing the concentration of nitrite. Let's take a look and see what happens in experiments 4 and 5. They doubled the concentration of nitrite, and the initial rate was also doubled. Between experiments 4 and 6, they quadrupled the concentration of nitrite, and they also quadrupled the initial rate of the reaction. The term rate law is an equation that shows how the rate depends on the concentration of the reactants in a chemical reaction. Equation 14.6 on page 565 shows that the rate is directly proportional to the concentration of both ammonium and nitrite. So you can see that the rate is equal to a particular constant, K, times the concentration of ammonium times the concentration of nitrite. So in equation 14.7, we see that the term K is the rate constant. The exponents M and N are called reaction orders. So we're going to take a look at the value of the rate constant from the data in the table. So to figure out the value of K, we're going to plug in all the information we know. So for example, in experiment 1, we have a rate of 5.4 times 10 to the negative 7 molarity per second. We have a concentration of ammonium, 0.01 moles per liter. And we have a concentration of nitrite, 0.2 moles per liter. We plug everything in, solve for K, and K is equal to a value of 2.7 times 10 to the negative 4, and the units are inverse molarity per time. So inverse molarity, inverse seconds. Even though we use the data from experiment number 1, does it really matter which experimental data that we use to calculate the value of K? And the answer is no, it does not matter. So whether we had used the data from experiments 1 through 6, we still, when we solve for K, would have gotten a value of 2.7 times 10 to the negative 4 inverse molarity, inverse seconds. So now that we have the rate law, and we can see that it's going to be rate equals K times concentration of ammonium times concentration of nitrite. And if we also know the value of K, we can calculate the initial rate for any set of concentrations. So for example, if we run this experiment with an initial concentration of ammonium of 0.1 and an initial concentration of nitrite that's also 0.1, we would get an initial rate of 2.7 times 10 to the negative 6 molarity per second. So these exponents, M and N, which are called reaction orders, we can learn some things about their value. If the exponent happens to be a 1, we say that the reaction is first order with respect to that reactant. Otherwise, if the exponent is 2, we say that the reaction is second order with respect to that reactant. Now the overall reaction order would be the sum of the exponents, the sum of the orders with respect to each reactant. In most of the rate laws that you will encounter in chemistry, the order with respect to a reactant will either be 0, 1, or 2. Letter J, is the statement below true or false? The exponent for each substance in a rate law should be the same as the coefficient for that substance in the overall balanced chemical equation. Well, this is a false statement. As you can see on page 566, we have first order for something that's N2O5 in equation 14.9, and yet there's a 2. As the coefficient in that balanced equation, there is a 2 next to the N2O5. So, although the exponents in a rate law are sometimes the same as the coefficients in the balanced equation, this is not necessarily the case. So the rate law must be determined experimentally. All right, letter K, is the statement below true or false? The exponents in the rate law should always be determined from experimental data. Yes, that is true. The best way to determine if a reaction is relatively fast or slow is to look at the magnitude of the rate constant K. This table gives us a summary of different examples of rate law. So the overall reaction order in the first example would be 0. And the units of the rate constant would have to be molarity per second. So the disappearance or the formation of a chemical over time, molarity per second. So for each rate law, we assume that the units of rate are molarity per second. Well, what if we have a first order reaction? The units of K would not be molarity per second. The units of K would simply be 1 over seconds, or inverse seconds, because you're multiplying A, which has units of molarity, times K, and you get molarity per second. So the units of K can be whatever they have to be to make the equation work out in terms of the units on both sides. So for our next example, we have a second order rate law. That would be molarity squared times K equals molarity per second. So K in this case would have to be inverse molarity, inverse seconds, so that the units would work out. So K can be whatever units it needs to be to make the units work out. Our next example is also a second order reaction. So first order with respect to A and B separately. Therefore, because it's second order overall, the rate constant would be the same, inverse molarity, inverse time. And then finally we have a overall third order reaction, so second order with A and first order with B. If we have molarity cubed multiplied by K to give you molarity per second, K, the units, would be molarity to the -2 power and inverse seconds. If we have a zero order rate law and you double the concentration of A, this would have no effect on the rate. If we have a first order rate law and you double the concentration of A, it would double the rate. If you have a second order rate law and you double the concentration of A, it would cause the rate to be multiplied by 4. In this particular problem, we need to figure out what the rate law is, and we have enough experimental data to do that. So we're going to analyze situations where they've held one species constant and they've changed the concentration of another species, and we can decide what effect this change in concentration has on the initial rate. So with respect to the mercury chloride, let's look for an experiment or experiments where they changed the concentration of mercury chloride, but they held the concentration of oxalate, C2O4, constant. Focusing on experiments 2 and 3, we see that the concentration of the oxalate was held constant, but the concentration of mercury chloride was doubled. As you go from experiment 3 to experiment 2, what did this doubling of the concentration of HgCl2 have on the overall initial rate? Well, the rate was doubled. So therefore the reaction is first order with respect to mercury chloride, because when they doubled the concentration of mercury chloride while holding the other material constant, it doubled the rate. Another way to show that the reaction is first order with respect to mercury chloride is to substitute the data from experiments 2 and 3 into the rate equation and solve for the exponent. So the exponent for mercury chloride would be equal to the following. We have 2 equals 2 to the m power. So therefore it is first order with respect to mercury chloride. So now that we know the order with respect to mercury chloride, let's talk about the order with respect to the oxalate, the C2O4 2-. Let's find a set of experiments where they held mercury chloride constant and only changed the concentration of oxalate. So comparing experiments 1 and 2, the concentration of mercury chloride is held constant, and as you go from experiment 1 to experiment 2, the concentration of oxalate is doubled. As a result, the reaction rate is actually quadrupled. It's multiplied by 4. So therefore, the reaction is second order with respect to oxalate. Another way to show that the reaction is second order with respect to oxalate is to substitute the data from experiments 1 and 2 into the rate equation and to solve for the exponent. So you can see that we now have an equation that looks like this. 2 to the n power equals 4. So therefore n is 2, and the exponent means that the reaction is second order with respect to oxalate. Okay, so the rate law must be showing that it's first order with respect to mercury chloride and second order with respect to oxalate. So rate equals K times concentration of mercury chloride times concentration of oxalate squared. The overall order would be 1 plus 2, or 3, and the value of the rate constant would come from our plugging in the data from any one of these three experiments into the rate law and solving for K. So if we choose experiment number 1, we have 5.2 times 10 to the negative 5th molarity per minute is equal to a rate constant K times 0.0836 to the first power and 0.202 squared. When we solve for K, we get a value of 0.0152. Now what about the units? We have molarity cubed times K equals molarity per minute. That forces the units for this particular value of K, the rate constant, to be molarity to the negative 2 power inverse minutes. Earlier we had talked about stoichiometry and mole ratios where you can change from the rate of one chemical to the rate of another. So we have in the table the rate of formation of chloride. And for experiment 1, that value is 5.2 times 10 to the negative 5th molarity per minute. If that is the rate of formation of chloride, what about the rate of disappearance of oxalate for that same experiment? Well, look at the coefficients for oxalate and chloride. It's 2 moles of chloride being produced for every 1 mole of oxalate being consumed. So the rate of disappearance of oxalate should be half as much as the rate of formation of chloride. If 2 moles of chloride are produced for every 1 mole of oxalate consumed, the magnitude of this rate of change of oxalate is half as much as that of chloride. So we have to put a negative sign to show that it's disappearing, and we have to multiply by 1/2, so we get negative 2.60 times 10 to the negative 5 molarity per minute. In the table, the rate of formation of chloride for experiment 4 was a question mark, but now that we know the rate constant, we can plug in those initial concentrations of mercury chloride and oxalate. We can use the value of the rate constant that we already have obtained and solve for the initial rate of formation of chloride for experiment 4. So there's our rate law. Rate equals K times concentration of mercury chloride times concentration of oxalate squared. We have our rate constant. We plug in those values in the table, so 0.0316 times 0.514 squared. Again, multiplying times the rate constant, and we get an overall value of 1.27 times 10 to the negative 4. It has the same units as the other values, which is molarity per minute. Section 14.4, the change of concentration with time. For a first order reaction, the rate law can be written as follows. Rate equals K times concentration of A. From calculus, the following integrated rate law can be obtained. That the difference between the natural log of the concentration of A at time t minus the natural log of the initial concentration of A equals negative Kt. So the meaning of each of the following terms would be that A sub 0 is the initial concentration of A at time 0. A sub t is the concentration of A at some later time t. K, you know, is the rate constant, and t is time. If we rewrite the integrated rate law, the first order rate law, so that's in the form of y equals mx plus b, we end up with the natural log of A at time t is equal to negative Kt plus the natural log of A sub 0. The following represents data from a first order reaction. So with the calculator we can do the natural log of 10, the natural log of 7.94, the natural log of 6.30, and fill in the remaining values in the table by just using our calculator and the natural log. Now that we have this data, we can plot the change in concentration over time, which is a curve, and the change in the natural log of the concentration over time. This is not a curve. This is a straight line. Look at the data. 2.30, 2.07, that's a difference of 0.23. 2.07, 1.84, that's also a difference of 0.23. So every single time we go down by 10 seconds, the change in the natural log of A is 0.23. So for a first order reaction, a straight line plot is generated by natural log of A versus time, and the slope of that line is equal to negative 0.023 inverse seconds. Notice that the unit is inverse time. We've already seen that the value of K has units of inverse time for a first order rate law. Doesn't matter which set of data we pick, we're going to get a slope of negative 0.023 inverse seconds. The value of this slope in the first order rate law equation is the rate constant. The absolute value of the slope of the line represents the rate constant K. And again, recall that the units of the rate constant K for a first order rate law are inverse seconds or inverse minutes. Now onto a second order reaction. The rate law can be written as rate equals K times concentration of A squared. From calculus, the integrated rate law would be 1 over A sub t minus 1 over A sub 0 equals kt. To rewrite that particular equation in the form of y equals mx plus b, 1 over A sub t equals kt plus 1 over A sub 0. Here is some sample data for a second order reaction. So we could calculate the natural log of all of these numbers, and we can calculate 1 over the concentration for all of these numbers. Now, are we going to get a straight line if we plot A versus time? No. Are we going to get a straight line if we plot natural log of A versus time? No. We are going to get a straight line if we plot 1 over A versus time. Let's take a look. So here is the graph of A versus time. That's a curve. Here is the graph of natural log of A versus time. That is also a curve. And here is the graph of 1 over A versus time. It's a nice straight line. So for a second order reaction, 1 over A versus time will generate a straight line plot. The slope of that line is going to be 0.005, and the units are inverse molarity, inverse time. The value of the slope is the rate constant, K. So recall that the units of the rate constant K for a second order rate law are inverse molarity, inverse time. So to sum up, we've talked about first order and second order. What about zero order? For a zero order reaction, the concentration is not going to affect the rate, and we can follow the disappearance of A over time, and we get a straight line. So concentration of A versus time will generate a straight line plot. They talk about zero order reactions here in this section, and you can see a straight line for a zero order rate law, and then you see a curve for a first order or possibly a second order. The most common type of zero order reaction occurs when a gas undergoes decomposition on the surface of a solid. If the surface is completely covered by decomposing molecules, then the rate of the reaction is constant because the number of reacting surface molecules is constant so long as there is some gas phase substance left. All right, we're still in this section, 14.4, change of concentration with time. Letter M, define the term half-life. Half-life is the time required for the concentration of a reactant to reach half its original value. The following exercise will help you to understand the concept of half-life for a first-order reaction. So remember that the integrated rate law for a first-order reaction is natural log of A sub t equals negative kt plus the natural log of A sub 0. If we substitute values of 150, so we began with 100 as our concentration and then we ended up with 50, then that value of t would be the half-life. So we end up with the natural log of 1/2 equals negative kT, and in this case, the half-life would equal 0.693 divided by k. That particular equation is very useful for a first-order rate law. Notice that the half-life for a first-order rate law does not depend on the initial concentration. To prove that, let's go back and look at the first-order data in Part C. It took 30 seconds to go from 10 molar to 5 molar. Well, how long did it take to go from 5 molar to 2.5 molar? Another 30 seconds. So the half-life for a first-order rate law is constant over time. If the decomposition reaction that you're looking at has a half-life that remains constant over time, then it has a first-order rate law. If you know that you have first-order kinetics, then the half-life will remain constant over time. So we have the equation 0.693 divided by k equals the half-life. That's for first-order kinetics. Remember that the rate constant k was 0.023 inverse seconds. We got that from the graph earlier. If we solve for the half-life, look at that. We get 30 seconds, so that definitely makes sense. That's consistent. If you know the rate constant for a first-order reaction, you can calculate the half-life. And if you know the half-life for a first-order reaction, you can calculate the rate constant. Again, a very useful equation. So it's only first-order kinetics that gives you a constant half-life over time. The half-life for a second-order reaction would not be constant over time. To prove this, we'll go back and look at the second-order data from Part H. It took a total of 20 seconds to go from 10 molar to 5 molar. To go from 5 molar to 2.5 molar, that took 40 seconds. So as you can see, the half-life is not remaining constant over time. If a decomposition reaction has a half-life that is not remaining constant over time, then you can prove that this would not be first-order kinetics. The half-life for second-order and other reactions depends on reactant concentrations and therefore changes as the reaction progresses. That's on page 575. Now moving on to section 14.5, temperature and rate. Most chemical reactions will occur at a faster rate when the temperature of the reaction is increased. If the temperature of a chemical reaction is increased, the value of the rate constant should increase. So if we have an increase in temperature, we will see an increase in the value of the rate constant K. So if the rate equals K times A and you increase the concentration of A, then you would expect the rate to increase. But that's for at constant temperature. What if instead you actually change the temperature and the rate goes up? Well, if you're holding A constant, the concentration of A is constant, something's going to have to increase. So when temperature goes up, the value of K will also go up. This discussion of temperature and rate relates to what's called the collision model in chemistry. So here are some important facts about the collision model. Molecules must collide with each other in order to react, and the greater number of collisions you have per second, the greater the reaction rate will be. It takes more than a simple collision to convert reactants into products. Not every collision results in the successful formation of a product. The two factors that will determine whether or not a collision will be effective is the orientation of the particles, so how they line up with each other when they collide, and the activation energy. Use the collision model to explain why increasing the concentration of a reactant should normally cause the reaction rate to increase. Well, when you have more molecules, then the greater number of collisions you have per second, the greater the reaction rate. So when you increase the concentration of the reactant, the number of collisions per unit time increases and the rate goes up. Why would increasing the temperature cause the rate to increase? Molecules are moving faster, they're colliding more often, and that's going to lead to a faster rate. From page 576, for any reaction to occur, it's not just enough to have a collision. Only a tiny fraction of the collisions actually leads to a reaction. So, for example, with hydrogen and iodide, when those molecules collide with each other, each molecule undergoes about 10 to the 10 collisions per second. Now, if every single time a hydrogen molecule collided with an iodine molecule, you got the formation of HI, the product, the reaction would be over in about a second, even less than a second. But reaction proceeds very slowly because only about 1 in every 10 to the 13 collisions actually is successful to produce a reaction. So what's keeping the reaction from occurring more rapidly? If we look at hydrogen and iodine, is it true that every single time a hydrogen molecule collides with an iodine molecule, you get a molecule of HI? No. In most reactions, the reactant molecules must be oriented in a certain way during a collision in order for a reaction to occur. And you can see that in this example. So when the chlorine molecule is your product, the two chlorine atoms have to collide and be lined up in the proper orientation. If a chlorine atom collides with an oxygen, the molecules just bounce off each other because they're not oriented in the proper way. Another situation is the energy. There is a certain amount of energy that is required for a reaction to occur, and this is known as the activation energy. When you see an energy diagram that climbs up a hill and then falls down on the other side, the top of that hill in the energy diagram is called the activated complex or the transition state. That is the sort of halfway point where bonds are partially broken and partially formed. You can see this in the following diagram as we fill in the different parts of this diagram. We have the potential energy of the reactants on the left. We have the potential energy of the products on the right. We have the activated complex at the top of the hill. The activation energy is the difference between where you start and the top of the hill. And the overall delta E is the difference between where you start and where you end. The rate of a reaction depends on the magnitude of the activation energy. The lower the value of the activation energy, the faster the reaction will be. So a relatively low value of activation energy means it's relatively easy for the reactants to be converted into products. But a high value of activation energy means a slow reaction. It's more difficult for the reactants to become products. So in this graphic example, you can see two different reactions. On the left, we have a low activation energy, so a fast reaction. And on the right, we have a higher activation energy, so a slower reaction. In terms of activation energy, explain why the reaction rate tends to increase at higher temperatures. Well, when you raise the temperature, you are raising the average kinetic energies of the reactant molecules. So a greater fraction of the molecules will have that minimum required activation energy. When you raise the temperature, that means a greater fraction of the molecules have enough energy to overcome the activation energy, and that leads to a faster rate. So at a higher temperature, a larger fraction of the molecules is able to reach the products because they have that minimum required activation energy. Which reaction is endothermic? That means it has to start at a certain level and finish at a higher level than where it started. So reaction number 3 is endothermic. The delta H for that reaction would be 5 kilojoules. Which reaction is the slowest? The one that has the highest activation energy, which is reaction 2. It has an activation energy of about 25 kilojoules per mole. And which reaction is the fastest? The one that has the smallest activation energy, and that would be reaction 1, which has a delta H of about 15 kilojoules per mole. So looking at the three reactions, if we went backwards to climb the hill from starting with products and going back to reactants, reaction number 1 in the reverse direction would be 25 kilojoules per mole. Reaction number 2 in the reverse direction would be 40 kilojoules per mole for its activation energy. And then for number 3, to climb that hill from products backwards to reactants, that difference to get up the hill would be 15 kilojoules per mole. Section 14.6, Reaction Mechanisms. At the beginning of this chapter, the term reaction mechanism was defined as a step-by-step, molecular level view of the pathway from reactants to products. Each event in a reaction mechanism is called an elementary step, and if there is only one molecule as a reactant in an elementary step, then that particular reaction is said to be unimolecular. If there are two reactant molecules in an elementary step, then it's bimolecular. It's unlikely for an elementary step to be termolecular or having three reactants because that would require the simultaneous collision of three particles. So that's very rare. So most elementary steps are either going to involve one or two reactants. Here we have a two-step mechanism. Step 1 involves the collision of two molecules of nitrogen dioxide, and then step 2 involves the collision of a molecule of carbon monoxide with a molecule of nitrogen trioxide. So the overall reaction involves adding steps 1 and step 2 together and crossing off anything that appears on both sides. So we cross off the NO2, well, one of them anyway, and we cross off the NO3. So the overall reaction would be NO2 plus CO to produce NO plus CO2. Now the species NO3 is neither a reactant nor a product, so therefore it was formed in step 1 and it was consumed in step 2. This is an example of an intermediate because it's produced in an earlier step and then it's consumed in a later step. So we call that an intermediate. On this energy diagram, you can see an intermediate in the valley at sort of the top of two hills, between those two hills, so where it is indicated by letter B in this diagram. An intermediate is not the same as a transition state. So the transition state would be the top of the hill. Transition states are unstable and can never be isolated, but an intermediate is something that is relatively stable and possibly can be isolated. If you know that there is the presence of an intermediate, it helps to support a particular pathway, a particular mechanism, and you can try to make some sort of a hypothesis about how the reactants are transformed into the products. So here we see an intermediate at step B, or the label on the diagram where it's the valley, and then transition states would be at the top of those two hills. Here we have a different two-step reaction mechanism. The first step involves a molybdenum compound, that's MO and then CO parentheses 6. And then the second one involves another molybdenum compound, that's MO parentheses CO5, plus a phosphorus compound. So in this proposed two-step reaction mechanism, the MoCO5 is classified as an intermediate because it's formed in step 1 and then consumed in step 2. CO would be classified as a product because it simply is produced on the right side in step 1, and then it just is going to be an overall product when we add these two steps together. In section 14.3, it was mentioned that the rate law does not come from the overall coefficients necessarily in the balanced equation, that the rate law must be determined from experimental data, and we've seen examples of that. One cannot determine the order with respect to a reactant by simply looking at the coefficient in the overall balanced chemical equation. However, if we are talking about the individual elementary steps of a reaction mechanism, so we're focusing on step 1, step 2, whatever the mechanism happens to be, then we can say that the experimentally determined rate law can be consistent with a reaction mechanism. So let's take a look at how we can look at the molecularity of an elementary step in a mechanism. So this means that if you have a unimolecular step, an elementary step that has one molecule, that would be first order. And if you have a bimolecular step, an elementary step that has 2 molecules, it is second order. So if we analyze individual elementary steps in a mechanism, then we can say that when it contains 1 reactant, it's first order, and when it contains 2 reactants, it is second order. A reaction mechanism often involves 2 or more steps. Each elementary step has its own rate constant, its own activation energy. And it's often true that one of the steps in the mechanism is much slower than the others. So the overall reaction rate will be limited by this slow step. The reaction rate cannot be any faster than the rate of the slowest elementary step. So we call this slow step the rate determining step. And this rate determining step will control the rate law for the overall reaction. So here we have a 2-step reaction mechanism, but now it's been labeled with relative speeds. So step 1 in this mechanism is slow, and step 2 in this mechanism is fast. So which one of these steps is going to be our rate determining step? Well, it's going to be the first step. The slow step is the rate determining step. Based on this mechanism, the overall balanced chemical equation, we've seen this before, is going to be NO2 plus CO producing NO plus CO2. So we now have the overall balanced equation for the reaction, and the rate is based on the slow step. Notice that the step 1 involves 2 molecules of nitrogen dioxide, so therefore it is second order with respect to the NO2. The rate of the overall reaction depends on the rate of step 1. It's bimolecular, involving 2 molecules of NO2. Now we can't actually take a picture of the reaction as it happens. We can't get some kind of a proof that the reaction occurs in a certain way. So when you have a mechanism, the mechanism itself can never be proved, but it can be stated that the observed rate law, which is coming from experimental data, is going to be consistent with that particular mechanism. So we can say that the mechanism that we're proposing is consistent with the experimental data. Now we have a 2-step mechanism involving a slow initial step where a single molecule of N2O is going to be involved as a reactant in the slow step. Let's write the overall balanced equation. So we cross off the O on both sides. So 2 molecules of N2O decompose to produce 2 molecules of N2 and 1 molecule of O2. Now look at that slow step. It's unimolecular. So therefore, the rate of the overall reaction depends on the slow step. The rate determining step only involves 1 molecule of N2O. So therefore, that particular rate would be first order with respect to N2O. So far, in the 2-step mechanisms that we've looked at, the first step was the rate determining step. Now let's take a look at an example where we have a 2-step mechanism, but the second step is slow. So we have an initial fast step involving 1 molecule of NO and 1 molecule of Br2. And then we have a slow step involving 1 molecule of NOBr2, which actually turns out to be an intermediate, and then 1 molecule of NO. Since step 2 is the rate determining step, we're going to write the rate law based on the 2 reactants that appear in step 2. Now, do you see a problem with writing this particular rate law? How can we control the concentration of NOBr2 if it's not a reactant? It's actually an intermediate. So we have 1 molecule of NOBr2. That's going to be a problem. We'll come back to that. And then we have 1 molecule of NO. We cannot accept the rate law written in part K as our final answer because intermediates, as we've talked about already, are actually unstable and we have no control over their specific concentration. We can't throw in this NOBr2 at the beginning of the experiment. So we have to rewrite this rate law to express it in terms of reactants only, so not intermediates. Let's go back to the first step. The first step was a rapid equilibrium. Remember that an equilibrium has both a forward rate and a reverse rate, and they are equal. So the rate of the forward reaction would be K1, so the rate constant, times NO and Br2, those concentrations, and that's equal to the rate of the reverse reaction. So I've written K -1, just the different rate constant, with the concentration of NOBr2. So the rate of the forward reaction is equal to the rate of the reverse reaction. Let's see if we can't substitute and solve for this concentration of NOBr2 by just simply rearranging the equation. When we do that, we get that the concentration of NOBr2 is dependent on the concentration of the reactants NO and Br2. And if we plug that into the rate law that we had written in part K, we have an overall rate constant times the concentration of NO squared and then the concentration of Br2. So what does this mean? That now we have a rate law for this mechanism which is second order with respect to NO and first order with respect to Br2. So we've substituted for this intermediate by writing an expression that says, hey, the first reaction was an equilibrium, it was a rapid equilibrium, so the rate of this formation of NOBr2 is governed by the concentration of NO and the concentration of Br2 in the first step. So our overall rate law is second order with respect to NO and first order with respect to Br2. Okay, so we've talked about intermediates. Let me remind you about a catalyst again. A catalyst is a chemical that will increase the speed of a chemical reaction without undergoing a permanent change itself. Let's see if we can find a catalyst in the following two-step mechanism. Well, there's some Br minus, there's some H2O2, and there's some H plus. And then there's Br2 produced, as well as water, as well as oxygen, O2. Let's cross off the chemicals that appear on both sides, and we add step 1 and step 2 together. We end up with an overall balanced equation that involves 2 molecules of H2O2 and producing 2 molecules of water and 1 molecule of O2. In this mechanism, Br2 would be classified as an intermediate because it is formed in step 1 and then later consumed in step 2. But the other chemicals, Br minus as well as H plus, those are classified as catalysts because they are present as reactants in step 1 and then they are later formed as a product in step 2. So a catalyst it is added at the beginning, but then you get it back at the end. So anytime you see a chemical in a two-step mechanism or a three-step mechanism that shows up as a reactant in an earlier step and then later shows up as a product at the end, that's considered a catalyst. A catalyst may function by stabilizing a transition state. Remember, the transition state is the top of the hill. This would lower the activation energy. So when you lower the height of that hill, you're lowering the activation energy, and that means that it's going to be easier for the reactants to be converted to products. So you're essentially making the reaction go faster by lowering the activation energy of a particular step. A catalyst can result in the formation of a new intermediate, and that might also provide a lower energy or faster pathway to get from the reactants to the products. Here we have an uncatalyzed pathway in red, and we have a catalyzed pathway in blue. So the faster pathway is the one that involves a lower activation energy. Another example of a catalyst comes from biology. A biological catalyst is known as an enzyme. And so an enzyme can stabilize the formation of some sort of transition state. They can bond to the substrate, and that can provide a lower energy pathway and a faster reaction. All right, well, that takes care of section 14.7, catalysis. It also marks the end of the chapter 14 packet. So I hope that presentation was helpful. Thanks for watching.